Hello everybody, this is Dr. Christopher White, and in today's presentation we're going to be looking at rocks, fossils and time. So it's quite a large presentation, so it's going to be split over two parts. Okay, let's get going. So unlike the other terrestrial planets, the Earth is a constantly changing system. So Mercury, Venus and Mars are, from a geologic point of view, pretty inactive, especially Mercury. So the rocks that we have on the surface of the Earth are constantly being eroded by wind and rain and ice and gravitational collapse, so the surface of the Earth is constantly being reshaped. We have continents that are moving around, sometimes they'll crash into each other, sometimes they'll rip themselves apart. We have sea levels rising and falling, we have massive volcanic eruptions, and we even have the odd meteorite strike. And all of these variables, can produce changes in the climate, or should I say the climate and the environment, on both a local, continental, or even in some cases on a global scale. So all the changes are not only reflected in the rocks which are formed, but also in the animals that were present, and therefore the fossils we observe. So sedimentary rocks are extremely helpful to us because the sediment itself is a direct reflection of the environment. But also on top of that, we have the additional information from the fossils. So the fossils will also help us to gauge what type of environment our sediment was being deposited in. So igneous and metamorphic rocks are useful for understanding what's happening at a local or regional scale, especially in the subsurface. However, their formation does not reflect climatic conditions. So there are a few occasions where igneous rocks can be somewhat helpful in gauging what was going on the surface of the Earth, but they're pretty few and far between. So the examples of those situations would be something like an extrusive rock, like a lava flow, especially if it's a mafic lava flow like a basalt. Well, when you look at the lava flow itself, you can tell, was that lava flow erupted onto the surface of the Earth, or was that lava flow erupted onto the seafloor? So not a whole lot of information, but it does tell you, whether you're in a marine or continental environment. We have pyroclastic deposits and volcanic mud flows, and they can be useful as well because sometimes when they occur, they can actually envelop and encase plants and animals, preserving them as part of the flow. And we can also have some large-scale eruptions that can have continental to global repercussions. So when there's a very, very large volcanic eruption, it can actually put so much ash into the high atmosphere that some of that ash will actually reflect sunlight back into space. And this can cause a noticeable decrease in global temperature. However, such an effect is typically only short-lived. It'll maybe last 1, maybe 2 years at most. So it's not really going to have a very significant effect on global environment. So when it really comes down to it, if we want to understand the surface processes, the environments at a local, regional, continental or global scale, your best option is to look at sedimentary rocks. And of course, the sedimentary rock is a direct reflection of the conditions in which the sediment is being deposited. So the sedimentary rock has indicators of the environment. Also on top of that, of course, sedimentary rocks are the dominant host for fossils, and fossils are extremely useful for geologists. So fossils are of course the basis of the geologic timescale, and they allow us to link together contemporaneous units. So, we've looked at your geologic timescale, all the boundaries between the different sections of it are defined almost exclusively by the first or last appearance of certain key fossils. Fossils are also helpful because they allow us to link rocks together of the same age. So if I have fossil A at a location, let's say Houston, Texas, and I find a rock somewhere else in the world, let's say Madrid, Spain, and that rock also contains fossil A, well, I can link those two rocks together using the fossils, and I can say, right, those rocks formed at the same time. Could have formed in completely different environments, but as long as they have the same fossil, we can say, definitively that, right, those rocks must have formed, contemporaneously with one another. So we obviously have the presence of certain fossils, which will vary by country, are used to define the geologic boundaries. Obviously that was before we had numerical dating methods. However, without firm dating methods, there was no way of gauging the temporal relationships between fossils. So this is obviously a bit of a problem. So if you have a sequence of rocks, you might look at that sequence of rocks and you think, right, well, this sequence of rocks, it's quite thick. Maybe it represents, 10, 20 million years worth of accumulated sediment. In reality, it could represent 1 million years of accumulated sediment. Or it could represent 500 million years of accumulated sediment. You don't know. If you can't date the rocks, you have no idea how much geologic time what you're looking at actually represents. And so that can lead to situations like this. So this is one of these classic diagrams you've seen. Chances are, in fact, you had a book like this when you were a child. It was a dinosaur book, and in it you had these pictures where you have all these different dinosaurs all interacting and doing their thing. The problem is that when you actually look at the picture and look at the animals in it and work out when the dinosaurs actually would have been able to exist, you very quickly come to the conclusion that they possibly couldn't have coexisted together. I mean, Tyrannosaurus rex was between 68 and 66 million years ago. Stegosauruses, on the other hand, 155 to 150. They would never have occurred together, ever. But this is one of the problems. If you don't understand the actual temporal relationships of the layers of rock, this kind of mistake can happen quite easily. So if I have a sequence of rocks, and in one layer from the Jurassic I have some Stegosaurus fossils, and then the layer directly above it I maybe have a Tyrannosaurus rex fossil, and I have no idea what the actual ages of those layers are, well, I look at one layer and I say, right, well, it's a Tyrannosaurus rex fossil directly above this Stegosaurus fossil, therefore chances are they existed at a somewhat similar time in geologic history. I would be completely wrong, but based on a very, superficial examination of the rock face, that could be the kind of conclusion you could come to. And this was one of the problems that faced early geologists. They just didn't understand exactly how much time the rocks they were looking at truly represented. So, by tying together observations from modern depositional environments, we can determine the likely conditions of formation for sedimentary rocks. So sedimentary geologists will go out to every depositional environment they can think of. And while they're there, they'll look at the different things going on. So they'll look at the type of sediment, what's the class size, how well rounded the class, how well sorted are the clasts, what are the clasts made from. Then they'll look at things like textures. Are there ripples? Are there mud cracks? Are there indicators of what's called a unidirectional flow? So, material is moving in just one direction, like a river. So, all this information will be gathered together, and what you end up with is a set of criteria which you use to define a sediment being deposited in a certain environment. And once you have those criteria, what you can then do is you can take them and you can look for the same things in rocks. And so if you manage to find a rock that meets the criteria you're looking for, well then you can say, right, well based on what I can see in that rock, that the sediment that formed that rock was deposited as part of, let's say, a delta. And so that's one of the great things about sedimentary rocks. The other great thing about them is if we know the likely conditions during the deposition of the sediment, well then we can identify the probable conditions in which any fossils that we observe within that rock would have lived. So once again, if we have our rock, which you've just discovered was part of a delta sequence, and we have fossils in it, well we can say, right, well clearly this particular animal liked to live as part of a coastal sequence associated with rivers depositing sediment. So the animal probably liked to live in quite shallow water, quite muddy water probably. So that's something that we can extrapolate by working out what where the sedimentary rock likely formed. We can then say, right, well any fossils that we find in this rock would have liked to have lived in these types of environments. In some cases we can actually get super lucky, because there are a few examples of species that appear to have not changed for millions of years, and these are termed living fossils. So to be clear, a living fossil will not be exactly the same as their ancestors. So, if we're looking at something like the horseshoe crab here, okay, this is a modern horseshoe crab, and this is a horseshoe crab from the Ordovician. So this is about 470 million years old. And so what you can see here is you can see that, look at the basic design, practically the same. So what you can do is you can extrapolate and you can say, right, well the reason the design hasn't changed is because the horseshoe crab is so perfectly suited to its environment. So that means once it's so perfectly suited, there's no push in terms of evolution to make it adapt. It's there, it's exactly what it needs to be. And so this means that we can look at a modern horseshoe crab and we can say, right, well, chances are this modern horseshoe crab is, lived in the same environment as this ancient horseshoe crab. So we can make that, link quite easily. And here we have a type of fish called a coelacanth. So this one's from the Devonian. So it's going to be about 380 million years old. And so once again, though, you can see the same basic design. Chances are that's because it became specialized to a certain environment. It's managed to, completely dominate that environment, so it hasn't died out. It's perfectly suited to it. And so chances are this coelacanth here lived in the same kind of environment as this modern example. So because the species has reached a point where only very, very minor adjustments could be made, it's highly probable that these modern examples lived in the same environment as the ancient examples. So by applying the principles of uniformitarianism and environmental limits set by fossil assemblages, which we observe, we can deduce the probable conditions during deposition. So when we're trying to understand the stratigraphic record, so the rock record, we must remember three things. Number one, uniformitarianism is king, because that's how we work out the environment in which sedimentary rocks formed. We use modern environments and we apply what we see in those modern environments to the rock record. We also need to remember that the geologic record at any one point on the Earth's surface will be incomplete. There is nowhere on the surface of the Earth where you have the complete sequence of rocks. Nowhere. And of course, we always need to make sure that any interpretation that we make has to be backed by evidence. We have to be able to prove, or at least firmly argue what we are proposing. Okay, so stratigraphy, a word which I have a lot of difficulty pronouncing. So it's a branch of geology primarily focused on sedimentary rocks. So it focuses on the origin of those rocks, the age of those rocks, the relationships between rocks, and the geographical extent of layered or stratified rock. So a layered rock is considered to be a stratified rock. So the same principles can also be applied to igneous and metamorphic rock. So if you think of a sequence of lava flows, you've got one lava flow on top of another, on top of another, on top of another. It's kind of like, it looks similar to a sequence of sedimentary rock. So you can apply the same principles. However, if you actually meet a geologist and they describe themselves as a stratigrapher, it in all likelihood means they work with sedimentary rocks. So stratigraphy is focused on relationships in both the vertical and the lateral. So vertical relationships are relatively straightforward. So as long as you have a good enough exposure, you can see what was going on. So you look at the rock at the bottom of the sequence, principle of superposition says that's going to be the oldest. And then you simply work your way up the sequence one layer of rock at a time. And you work out what depositional environment each layer of sedimentary rock represents. So vertical relationships are very straightforward. Now, lateral relationships, on the other hand, are often a little bit more difficult. So in order to work out what's happening to a layer of rock, and let's use our sandstone here as an example, we would need to travel to multiple locations. So if we're just looking at the vertical relationship, we could just stand here at the bottom of this cliff, look at the sequence there, and we could work out, what was going on in the vertical. However, horizontally, we would need to go to multiple locations and track the same layer of rock. And as we know from the principle of lateral continuity, eventually the layer of rock will pinch out and disappear, or it will terminate against some kind of basin margin. So this is why lateral relationships are quite difficult, because you have to go to multiple locations, and in some cases, the locations you would like to go to just aren't there. They've been completely eroded away, so the layer of rock will just completely disappear. So this is a bit of a problem for geologists. So let's start by looking at the vertical stratigraphic relationships. So individual layers within a sedimentary sequence are either defined by sharp contacts, which we call bedding planes, or gradational contacts. So if we look at this picture down here, we can see we have two distinct layers of rock. We have this darker, rubbly looking layer, which is a conglomerate, and then above it we have this blocky kind of pinkish white layer, which is a limestone. And you can see between them we have this nice sharp boundary. That's our bedding plane. So when you are looking at a rock face, you can pick out the individual layers quite easily. And that's because as you go from one layer of rock to another, there's going to be some kind of change, and you can see those changes. So the changes that we see could be something like composition. So if we look at this picture down here, well, what can we see? Well, we can see down here we have a rock that's made from quite large chunks of rock. In contrast, this rock up here is made from calcium carbonate. So we have a difference in the rock chemistry. We also have a difference in the texture. We can see this has a very rubbly texture. This has a very massive and uniform looking texture. And obviously we have differences in the colour as well. This one's this kind of black brown, and this one is this kind of pinkish white. So, just by looking at the picture we can see here, we can quite easily, distinguish between the two layers. We don't even realise we're doing it. When if you look at it just for a second, you won't realise what criteria you're using to distinguish between the layers. All you know is that you can distinguish between them very easily, and it's because one or more of those variables will be changing, and that allows you to see the change. So when we're looking at sequences of rocks, it's the variations in these three factors which will make the different layers look different. Okay, so we can discern them from one another. So when we have these sharp boundaries, it can reflect a few things. Number one, it could reflect a rapid change in sedimentation. So for instance, if we have an environment where, let's say we're off the coast, we're underwater, but the environment's quite stable. Well, that's an environment where, it's quite low energy. We might have lots of muds being deposited. So we might be in a marine mud-dominated environment. Now then, every once in a while, what might happen is there might be a big storm come in. And that big storm will churn up the water, and it might cause some of the more sandy sediment from closer to the coast to slide down the continental shelf. And so what will happen is all of a sudden our muddy environment will suddenly have a layer of sandy material dumped into it. So there was a very sudden change in sedimentation. We went from nice, peaceful, muddy environment to a high energy environment into which this sandy material is being dumped. And obviously that's going to lead to a nice sharp boundary between the two layers of sediment. A sharp change could also represent a period of non-deposition. So if you have a situation, for instance, if we just go back to the previous picture, let's say for a period of time we have this conglomerate forming, and then sedimentation stops for a while. Nothing's really getting eroded, nothing's being deposited, so everything just pauses for a little bit, and then this layer of sediment gets deposited over the top. Now, these periods of non-deposition could last simply from minutes through to years, but from a geologic point of view, they're insignificant. And then, of course, we have periods of erosion, which of course produces unconformities. So in that case, if we just go back to this previous picture, in the case of an unconformity, there could have been a whole sequence of rocks here. So there could have been a conglomerate, then a sandstone, then a mudstone, then a limestone, but all that stuff above the conglomerate here got eroded away, so it's gone, it's lost, and then this limestone gets deposited over the top. And so this contact here would represent the unconformity, and it would of course represent lost rock and therefore lost time. But once again, you would end up with a nice sharp contact. So in terms of the other option, which is graded bedding will reflect a gradual change in the conditions of sedimentation. So such changes could reflect a variation in energy. So think of a river flooding. Well, when the river floods, the water comes out of the river and it leaves the river with quite a lot of energy. Okay, so it's carrying a lot of sediment with it. The water's quite energetic. Now, because it has lots of energy, that means it can move quite a large range of clast sizes. It can move small clasts and it can move medium-sized clasts. The problem is as soon as the water starts leaving the river channel, all of a sudden it begins to slow down quite quickly. And as the water begins to slow down, first of all it has to dump the large clasts, and then as the water gets slower, it'll then dump the next size of clast, and then steadily over time, as the water gets lower and lower energy, finer and finer material will be deposited. So, when a river floods, you might get a sequence that goes medium sand, very fine sand, silt, clay. So coarse sands the medium coarse sands at the bottom and the clays at the top, and that's just a result of the energy of the system steadily changing, going from a high energy initially to a low energy at the end. We also get gradational contacts when we transition from one depositional environment to another, if they're contemporaneous with one another, so if these two different environments are operating at the same time. Okay, so let's think of unconformities. So if you remember, there are four types of unconformity: disconformity, angular unconformity, nonconformity, and paraconformity. Now, paraconformities are a bit of a pain to identify, so most of the time when we talk about unconformities, we're only really talking about the first three: disconformity, angular unconformity, and nonconformity. So when you're standing in front of a cliff and you can see that you have one layer of rock, and maybe let's say this first layer of rock is 200 million years old. Then the layer of rock above it, you can date that, and it's 150 million years. Well, that means the contact between those two layers of rock has 50 million years of lost material. One layer was 200, the next layer was 150, therefore there's a 50 million year block of time missing. So that's our unconformity. Now, that is perfect when you are just looking at one location. However, stratigraphy says we don't just look at sedimentary rocks vertically, we also have to look at them laterally. So in some cases, some unconformities can be absolutely massive. They can cover entire continents. So there are some unconformities in North America that will literally go all the way from the west coast across to the east coast. They're huge. The other thing about unconformities is that an unconformity does not represent the same amount of lost time at every location. So over here on the right, we have some wonderful diagrams produced by yours truly. And we can see, here we go. So here we have ourselves a little continent, and it's surrounded by the ocean, and this dashed line here represents the edge of the continent, which is underwater. So this green area is the bit that's exposed. Well, as it's exposed, that's the area that's undergoing erosion. Then steadily over time, the sea level drops, and so more new land is exposed. So this area is now undergoing erosion, but the bit in the middle that was exposed first, well, that's undergone more, so it would have lost more rock. And then over time the sea level retreats until the continent is completely exposed. And by this point we'll have an unconformity running from one side of the continent to the other, because everything's exposed, it's being eroded, and so we're losing a rock. So we're forming our unconformity. However, the unconformity does not represent the same amount of lost time at every location. So in this area in the centre here, which was exposed first, we're going to have an unconformity which represents a significant amount of lost time, because lots of rock has been eroded. In contrast, the rocks out here, well, they will have suffered a lower degree of erosion, and as such you will have lost less material, and so the unconformity out here will represent less lost time. And so we need to remember this, that when we're talking about stratigraphy, we're not just thinking in the vertical, we're also thinking in the horizontal as well. And this applies to unconformities just as much as it does to layers of sedimentary rock. So we need to think about things which we call facies, or sedimentary facies. So first of all, we need to think about how sedimentary rocks will change laterally. So a facies is simply an environment which will lead to the deposition of a distinct sediment, which will form a distinct sedimentary rock. So for instance, if you want to think of different facies, so let's think of a coastal facies. So let's think of a sandy beach facies. Well, in that environment you have a beach environment. It's moderate to high energy. There's lots of sandy material there. And so, we know that environment is going to be a sand-dominated environment. We're going to see ripples, we're going to see fossils, all that kind of stuff in this environment. So we can look at that package of rock and we can say, yes, this package of rock formed in a, coastal beach environment. Now then, as we move into deeper water, so we're going down the continental shelf, eventually the water will steadily become less and less energetic. So we'll transition from a higher energy sand-rich environment closer to the coast, and we'll move into a lower energy mud-rich environment further out. Now, obviously, now we have a completely different type of environment, which is going to produce a completely different sediment. The beach environment produced a sandy sediment because it was, moderately energetic. The low energy environment, on the other hand, is going to have a mud-dominated sediment. And so, simply by looking at these different sediments, we can tell we've transitioned from one environment to another. We've moved from the moderate energy environment to the low energy environment, and we can see that because the rocks change. So, the question then is well, how did the transitions between these facies actually occur? Well, the transitions can occur in one of four ways. First of all, it can be an abrupt transition. So you can simply have your rock is cut by a fault, or it reaches some kind of barrier. So your layer of sediment will just simply butt up against something, and it can't go any further. So a classic example of that would be something like a river. So in your river channel, where the river is actually contained, you obviously have your sequence of river sediments, your channel sediments. Then as soon as you step out of the river, those channel sediments are stuck in the river channel, aren't they? They can't get out. So as soon as you step out from the river channel, you're in an environment of the floodplain environment. So now you're out of the water and you're into a dry environment. So in that case, we have an abrupt transition. The edge of the river channel, the river sediments stop at the edge of it, and then you transition into a new environment. Another thing that can happen is your layer of sediment can steadily get thinner and pinch out. So obviously the further you go from the sediment source, the less material there's going to be, and so your layer of sediment is going to steadily get thinner and thinner and thinner, and eventually that layer will simply pinch out, disappear, and a new layer of sediment will take its place. Now we also have something which is called intertonguing, and this is where we have multiple layers of rocks, and they produce a distinct zigzag pattern. And it's the result of sea level change. Now, I'm not going to worry about it too much because in a few slides' time I have some reasonable diagrams which hopefully will show you what's going on in a reasonable level of detail. A far better level than I could possibly explain it. And finally we have lateral gradation. And that's when your layer of sediment slowly grades into a new sediment. So as our medium energy beach sediment which is very, very sandy, might steadily become more and more and more mud rich as we move from medium energy to low energy. So as you move from the medium to the low energy environment, the amount of sand decreases and the amount of mud increases. And you have this gradational change going from the sandy beach sediments to the muddy low energy sediments. So both intertonguing and lateral gradation indicate the simultaneous operation of different depositional processes in adjacent environments. So in both of these instances, what we have is we have two different depositional environments right next to each other at the same time. So a good example is the one we've been discussing, the continental shelf. You'll have a sandy environment closer to the coast, which is the higher energy nearshore environment, whereas you'd have muds deposited further out to sea in a much lower energy environment. And so if the environment facies will grade into one another, the layer will become more mud rich. So if this is a very simplistic diagram, is just trying to show that process. So here we have our moderate to high energy beach environment, which is sand dominated, and here we have our low energy mud rich environment. Well, in the case of a gradational boundary, you're going to see the amount of sand will steadily decrease as we move this way, and the amount of mud will steadily increase. So if the processes in these two environments operate independently of one another, however, you're going to get a sharp boundary. So in this case, the two environments are operating kind of together. There's this gradational zone between the two where both environments overlap. There will be some instances, though, where these two environments will operate completely independently of each other, and that's going to produce a sharp boundary. So it's going to be sand-rich, boundary, mud-rich. Okay? And in that instance, we're going to see indications of things like intertonguing in our sedimentary sequence. And this intertonguing, this zigzag, as I said, is the result typically of sea level change, or it can also be the result of short-lived changes, so things like hurricanes or landslides causing the positions of the boundaries to shift slightly over short periods of time. So here's our situation. So this is what we've been talking about. Here's our continent, here's our coastline, and we can see as we move into deeper water, we go from a sand-dominated environment, because this is a moderate energy environment. We then transition into a low energy, mud-dominated environment, and then we step out into a carbonate-dominated environment. So this is the classic set of rocks we expect to see on a continental shelf. Sandy, closer to the coast. As we go into deeper water, they transition into muddy, and then finally the mud will give way and it will be replaced by carbonates. And so if we would just take a slice through this, what we would see is we would have a sequence that goes carbonate, or limestone facies, mud facies, sand facies, and then continental facies, the land itself. Okay, so if we just moved across here, that represents that. This represents this. From there to there represents this. And this bit is represented by the continental facies. So what I'm going to do is I'm going to change the sea level. So I'm going to push the sea onto the land. So now all of a sudden your land is going to be covered by a moderate to high energy beach environment. So our continental facies are going to start to be covered over by the sand facies. At the same time, as the sand facies starts moving inland, the mud and carbonate facies are going to follow it. And so we're going to see the mud facies superimposing themselves over the top of the sand facies, and the carbonate facies over the top of the mud facies. Okay, and we can see that as the water's moving inland, we have these facies are moving over the top of each other. Then there's going to be a marine regression. The sea is going to start coming off the land and go back into the oceans. Well, in that case, all of a sudden, your land, which was covered by water, is now exposed again. So now it's a continental environment. So we're going to see the facies change. We're going to get different rocks forming. Obviously, as the sand facies moves back into deeper water, the mud facies will also move back into deeper water, and so will the carbonate facies. And so we'll see the facies move away. Then there will be a change in sea level again. We'll see the sea level moving inland, and then we'll have the facies begin to move inland. So once again we have the sand facies moving over the top of the continental facies, and you can see this happening. So we've got it moving on land, then we have a reversal, and then we have another marine transgression. And so what you can see here is there's that zigzag pattern, that intertonguing that we were talking about. So as the sea level changes, it causes these facies to shift position, and they'll superimpose themselves over the top of each other. And it leaves this very, very distinct zigzag pattern when you look at the facies vertically. And so I appreciate it's an absolutely terrible picture, but you can see that going on here. So over here we have a mud facies in this kind of grey-brown, and here we have a sand-dominated facies in this kind of yellow-white. And you can see we have these zigzags, so it comes out here, steps back, comes out a long way, steps back, comes out again, steps back. And this is a facies superimposing itself over another. So in this case we have the sand facies superimposing itself over the top of the mud facies. So if we just go back, we have a sand facies superimposing itself over the top of a mud facies. So this is probably going to be produced by a marine regression. Okay, and this diagram here kind of just summarizes the differences. So obviously when we have lateral gradation, we change from one sediment to another gradually. In the case of intertonguing, we have distinct facies which have sharp boundaries, hence the sharp contact. And in the case of a layer of rock, it will typically thin and pinch out over time and disappear. We've also discussed, of course, that rocks can also terminate when they hit some kind of basin margin, some kind of vertical surface. So no layer of sedimentary rock will continue indefinitely. It will always have to terminate in some way. It'll either be a sharp termination or it will grade into a new layer. Okay, so we're going to stop the first part here. So once again, get up, have a walk around, get a drink, sit down for a few minutes, relax, and then come back for part 2.